All right, Ninja Nerds, in this video, we're going to talk about leukopoiesis. So like every video, let's first off decipher what is leukopoiesis. Leukopoiesis is so leuko means white, it's our white blood cells, right? So leukopoiesis is the formation, poiesis is formation of white blood cells. That's what we're going to talk about in this video, is we're going to talk about the formation of white blood cells. So let's go ahead and dive right into it. So first off, what we're doing here is we're taking specifically a section of a bone here and zooming in on it super deep so we can see at the molecular and cellular level. Okay, so where does this actually occurring? Again, same place that it's occurring in erythropoiesis and thrombopoiesis. It's occurring in the red bone marrow. Okay, so within the epiphyses of the long bones is a good common place for that, with the trabeculae, right, the spongy bone. All right, so we're diving in right in there and we're going to zoom in. So let's get started. All right, so first off, we have a stem cell for all of the blood cells within the entire body. What is that stem cell called? That stem cell that we're going to start off with right here, look at this guy right here. This stem cell is called a hemocytoblast. Okay, a hemocytoblast, but they also can call it a pluripotent stem cell. You can even call it a hematopoietic stem cell. I'm just going to put a hemocytoblast. Okay, so this is our stem cell for all the actual cells within the body. Well, what happens? This hemocytoblast is constantly dividing, and it's dividing into two different cell lineages. Look at this. So one of the cell lineages that it's going to form is what's called a myeloid stem cell. Okay, so it's going to form a myeloid stem cell. The other one that it's going to form is called a lymphoid stem cell. Okay, so two different types here. Again, what is this one right here? We're going to say this is the myeloid. And this one down here is going to be the lymphoid stem cell. Okay, so these are stem cells. All right, so now, myeloid and lymphoid stem cells, right? First off, myeloid can divide into a bunch of different things. Real quickly, what can it divide into? Okay, so a myeloid stem cell, what can it divide into? If you remember, myeloid stem cell, it can divide into three different cell lineages. One is going to go to form red blood cells, one is going to go to form platelets, and the other one is going to go to form what we're talking about, which is granulocytic white blood cells and monocytes. Okay, so what we're going to focus on is this step right here, but we will do a brief introduction into platelets. Okay, but we're focusing on this one right now, the granulocytic white blood cells and the monocytes. So then what happens? This myeloid stem cell is going to start dividing. It goes into two different lineages, I told you, right? One is for the granulocytic white blood cells and one is for the monocytes. But real quick, how do we know? How does this cell know to go into forming red blood cells? How does it know to going into forming platelets? How does it know to going into forming granulocytic white blood cells versus monocytes? It's all about the hormonal or chemical factors. For example, we already know that red blood cells depend upon EPO, erythropoietin, right, as well as the other nutritional factors. Platelets depend upon what's called TPO, which stands for thrombopoietin. We'll talk about that because it's made by the liver and the kidneys. And granulocytic white blood cells and monocytes, what do they depend on? Now we can focus on it. Okay, so let's say that this step right here is going into forming our monocytes. And this one down here is going to form the granulocytic white blood cells. So what needs to happen in this step? Well, we need specific chemicals. We need interleukin 3, we need interleukin 5, and we need what's called a granulocytic colony stimulating factors. And the reason why we need a granulocytic colony stimulating factors is because monocytes are agranulocytes. What does that mean? That means that they have granules, but they're not visibly seen whenever you provide some type of right stain on them. Okay? They do have granules, but they're not visibly seen whenever with a right stain. All right, next thing. So these are going to drive this step. So what's the overall cell going to be then? This cell is actually going to be a monoblast. So what is this cell called here? This cell is called a monoblast. And then what happens is this monoblast, it's now committed to becoming a monocyte. So what happens here? This cell starts actually converting itself into what's called a pro-monocyte. So it's going to start turning itself into a pro-monocyte. monocyte. So his nucleus was it's getting ready to start forming these constricted shapes, right? So this is called a pro-monocyte. Then what happens? It turns into a monocyte. So then it becomes a monocyte. And then one more thing can happen. This monocyte will go into the blood, right? So we're going to show it going into the bloodstream. But when it leaves the bloodstream, so we'll show that here in a second, it actually goes out into the tissues and becomes a macrophage. But we'll talk about that in a second. All right, so again, what is this last one here? This is a monocyte, okay? We'll come back to this one. Next one, myeloid stem cell. What is this guy going to need in order for this event to occur? He's going to need, same thing, interleukin 3, interleukin 5, but he doesn't need a granulocytic, he needs granulocytic colony stimulating factors. Granulocytic colony stimulating factors. There is other chemicals that the monoblast would need, but we're not going to go into that, okay? We're going to just keep it very, very general, all right? So these chemicals are needed in order to drive this process, okay, with granulocytic colony stimulating factor being one of the most potent effects. So now what cell do we have? Now we have a myeloblast. So what is this cell here called? This cell is called a myeloblast. Okay, here's where we get to the good stuff. The myeloblast, what happens to him? This myeloblast can actually go and divide into 3 different cell lineages. So now he's going to divide. So look at him. He divides into 3 lineages here. One of them is actually going to be of like a basophilic effect, right? So one of them is going to be more of a basophilic. We're going to talk about this one. The other one is actually going to be more of an eosinophilic, and we'll talk about him. And the other one's going to kind of be a little bit more of the neutrophilic, right? The other one's going to be a little bit more of the neutrophilic, and we'll talk about this one. Okay, so again, the myeloblast divides, and it divides into 3 different cell types. This one up here, now first off, when they go from the myeloblast, they're going to go into what's called for specifically myeloblast, they're going to what's called a promyelocyte. So myeloblast to what's called a promyelocyte. But each individual one is different. So we're going to call this one right here, we're going to call him a basophilic, right? Promyelocyte, right? That's that first one. The second one is going to be eosinophilic, and I'll explain what this means. Eosinophilic, promyelocyte. And then the last one down here is going to be a neutrophilic. Neutrophilic, promyelocyte. So what happens here? The genes get activated within this guy, this basophilic promyelocyte, and then that's going to turn into a specific type of cell, which is now, remember, when it goes from pro, it always goes to the next thing. So promyelocyte to a myelocyte. So what's the next thing that's going to happen? This basophilic promyelocyte will then convert into a basophilic myelocyte. So now the next step over here is going to be the basophilic myelocyte. Now the nucleus is starting to get ready to constrict, but it hasn't constricted yet. It's starting to form more of a U shape at this point in time. So now it's kind of U-shaped maybe, might be U-shaped, so let's kind of show that here. Okay, and then it might even have some blue granules that are being present. Okay, and what do I mean by blue granules? That means if you apply a right stain, what color would this actual granule show? They would show more of a bluish color because they take up the methylene blue base. So again, what is this one called? This is called a basophilic myelocyte. Now, what happens to this eosinophilic one? The eosinophilic one, same thing. It's going to take up that, kind of like a U-shaped. It hasn't completely segmented its nucleus yet. And then it's going to take up these red granules, which is going to be due to the red eosin acid. So it's going to take up that red eosin acid. So this is an eosinophilic myelocyte. And then last but not least, right, is the neutrophilic myelocyte. What happens to him? Again, he takes up more of that U-shaped nucleus, right? And this is going to be called the neutrophilic myelocyte. Then what happens? The basophilic myelocyte will finish up that actual U-shaped constriction. So it'll start finishing up that U-shaped constriction here. So now this basophilic myelocyte is going to start finishing up that U-shaped constriction, and it'll take on a full U-shape, a perfectly formed U-shaped nucleus. So it's beginning to start within the myelocyte form. Again, all of these are beginning to form. I should actually make these a little bit bigger because they're not completely U-shaped yet at this point in time within the myelocyte, right? They're beginning to form that U-shaped. But then as they get ready to go into this next one, they should now have a perfectly constricted U-shaped nucleus. So now what is this one? Here we have this one. Here we have this one. And this last one we have right here, right? So now what it should look like? It should be perfectly U-shaped. Perfectly U-shaped nucleus now. And this one should have a perfectly U-shaped nucleus. And then this last one should have a perfectly U-shaped nucleus. So again, they're starting to form that U-shaped nucleus within the actual myelocyte, but they completely form that constricted U-shaped nucleus within this next step. So now this is called a band cell. Okay? What is the difference between a band cell and a myelocyte? It's that they complete that constricted form of the U-shaped nucleus. So now it's a completely formed U-shaped nucleus. So this is called a basophilic band cell. What would this one be? And again, what will it have? The nice blue granules in here. This one will have the nice red granules. And this one would have the nice, this one I would obviously take up, and I'll talk about this again in a second when we get to their functions. The neutrophil would actually take up more of a blue and red. So again, over here it would actually have a blue and red granules. We'll show that though when we get over there. So again, what is this one called? Eosinophilic band cell. And this last one over here is a neutrophilic band cell. Neutrophilic band cell. Okay, now we come into the final stage. After this, they take on their ending form, their true form, and this is when the nucleus completely constricts and segments. So what does that mean that it segments? It means it forms multiple nuclei. It forms multilobated nuclei, or different shaped nuclei. So what happens with the basophil? The basophil, whenever its nucleus segments and constricts completely to get rid of that U-shape, it can keep the U-shape, but some of it can actually form a S-shaped nucleus. So it can have a nice U-shaped nucleus still, or it can form an S-shaped nucleus. So again, that's the difference between this one. It's segmented now. That differs the band cell from this next cell, which is now a basophil. So a basophil is just going to have a segmented nucleus, which can either remain U-shaped or it can take on a S-shaped. So this is a basophil. The eosinophil, it likes to form a bilobe nucleus. So if you look here at the eosinophil, he likes to form a bilobe nucleus. It kind of looks like an old telephone pole, or you can imagine as like glasses, right? It's kind of like cool, right? So again, he takes up that red eosin acid, and that's actually going to be our eosinophil. Okay? Last one here, the nucleus is the best at segmenting. He loves to segment into lobes. He's actually called a polymorphonuclear leukocyte. He can have 3 to 5 lobes. So look what happens to this guy. He has, I'm going to just draw 3 lobes here, but he can have even more than that. And again, I'm going to kind of change a little bit from here so that we stay consistent when we get over here. What kind of granules does neutrophils have? What color do they take up? And again, I'm going to change the color, but remember, it should have been that color the whole time. It would be, he takes up methylene blue base, because he has affinity, the granules have affinity for methylene blue base, and some of his granules might have affinity for red eosin acid. So he would actually take up more of a, he would have more of a pinkish cytoplasm because it's going to be a neutral color between the acid and the base. So it's going to be a nice pink color. So again, what is this cell right here called? This is now called a neutrophil. Okay, so what cells have we helped to form so far? We now have over here the monocyte, right? with no visibly stained granules, but he still might have granules. So we have monocyte here. Okay, one more cell line and within this myeloblast, and then we're going to go over into the lymphoblast. All right, so what did I say before? Myeloid stem cell can form granulocytic white blood cells, monocytes, and they can form platelets. We've already done red blood cells. We already know erythropoiesis. Let's quickly do thrombopoiesis very quickly. So again, what's another cell that this guy can divide into? He can also come into another cell lineage. And what is that cell lineage called? That cell lineage is actually going to be forming what's called what is this cell here called? This is called a megakaryoblast. A megakaryoblast. What drives this step? Just like what drives all of these other steps? Thrombopoietin. So bear with me, thrombopoietin. Okay? And this is made by who? The liver and the kidneys. So the liver and the kidneys secrete thrombopoietin. And thrombopoietin drives this step right here to convert the myeloid stem cell into the megakaryoblast. Just like every other one, we always go from blast to pro to cyte, right? Same thing. So what does this guy become? Next thing is going to happen is he's going to form what's called a pro-megakaryocyte. So what's this next one? It's called a pro-megakaryocyte. Then what happens? The pro-megakaryocyte will turn into a megakaryocyte. And then what will happen from there? So again, this is called a megakaryocyte. And that megakaryocyte will then get converted into what's called a platelet. So then that's what we're going to go into in this next step. So again, we went megakaryoblast, pro-megakaryocyte, megakaryocyte, and let's draw this megakaryocyte right over here so we can show some room here. So what is this one right here? Again, this is called a this is called a megakaryocyte. And this cell is huge. He is very, 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 very big, like huge. Okay, so we've done the megakaryocyte. Let's come back over here and let's finish up with the lymphoid stem cells. All right, so now, what happens here? Lymphoid stem cell, thankfully he doesn't divide into too many different cells. We're not going to go over the natural killer cells in this one, but they could also divide. But we're just going to do for right now, we're just going to go into specifically our lymphocytes. So now this lymphoid stem cell, what happens to him? He goes into forming what's called a lymphoblast. So let's draw that with, let's do that black actually. So again, what is this cell right here called? This is a lymphoblast. Okay, so lymphoblast right here. Now, just like everything that we've done so far, what drives this step? Same thing, interleukin 3, interleukin 5, but here's the big thing. Lymphocytes are agranulocytes, so they wouldn't need colony-stimulating factors. They would need granulocytic colony-stimulating factors. Okay, and this would drive this step right here. Okay? So now, interleukin 3, interleukin 5, and agranulocytic colony-stimulating factors can drive the lymphoid stem cell to becoming a lymphoblast. Now what happens? That lymphoblast, he's going to start undergoing some specific proliferation and differentiation, and then he'll become specifically a prolymphocyte. So then the next cell we're going to have here is a prolymphocyte. A prolymphocyte. So what does someone call it? A prolymphocyte. And then what happens with the prolymphocyte? The prolymphocyte will then become a functional lymphocyte, but not completely. So let me actually rephrase that. One of the lymphocytes will be functional at this point in time. Okay, so now we have a prolymphocyte into a lymphocyte. Now here's where it differs, and I'm going to go into more detail when we show it in the bloodstream. The lymphocyte here that leaves the blood and leaves the bone marrow through the sinusoidal capillaries and goes into the bloodstream, where it will reside in other lymphoid organs, is going to be the B lymphocytes, because that's the mature one. right? So there can be two cells here. One is going to be the B lymphocyte. B lymphocyte. And the other one is going to be the T lymphocyte. T lymphocyte. The B lymphocyte, when it leaves the bone marrow and goes into the sinusoidal capillaries, it's functional. The T lymphocyte is not. The T lymphocyte will have to go to a gland, a lymphatic gland or lymphoid organ, a primary lymphoid organ called the thymus, where it will mature and undergo selective processes and then get put into the bloodstream to go into secondary lymphoid organs. We'll talk about that in more detail in immunity. All right, B lymphocyte. So where's it going to go? These two cells are going to go out here, right? So let's just show, we're going to go over there and show these two cells coming out over there. All right, now let's bring all of these cells and put them into the bloodstream and talk about their functions. All right, so again, what cells are going to be leaking out of here? Monocyte's going to be coming out here, right? So now we'll have a monocyte. We'll talk about him first, right? So we'll have a monocyte right here. He'll be the first one we'll discuss. The basophil. The basophil will actually come out here. He'll be the second one we'll discuss, right? He's got the S-shaped nucleus with the blue granules that stain from the methylene blue base, right? And then we'll talk about the eosinophil. So then we'll talk about the eosinophil after that. So again, the eosinophil has bilobe nucleus. You can remember because it looks like he has like little sunglasses on, right? And he takes up the red eosin acid. Talk about him. Then we'll talk about the neutrophil. And if you remember the neutrophil, whenever it goes on the segmentation, it can form polymorphonuclear leukocytes, which means it just has multiple lobes. So again, here's that guy right there, right? There's our multiple lobes here. Let's even draw another one there. And then again, he takes up both the methylene blue base and the red eosin acid. So he's going to have more of a pinkish cytoplasm, right? And then again, what's the other one? The megakaryocyte. Here's where I want to say something real quick. The megakaryocyte. First off, the capillaries that are present within the bone marrow are what's called sinusoidal capillaries. So really important, these are called sinusoidal capillaries. Okay, sinusoidal capillaries. These are very important because they're very, very permeable, large intercellular clefts. Well, they're not large enough because the megakaryocyte is a huge, huge cell. So when it tries to be able to squeeze through the sinusoidal capillaries and tries to get into the bloodstream, it actually gets stuck. And then what happens is it actually fragments, it explodes. And when it fragments into very, very many cytoplasmic fragments. What are these cytoplasmic fragments called now? These cytoplasmic fragments are called platelets. So that's what these are now. All of these cytoplasmic fragments that megakaryocyte ruptured into is now called platelets. Okay, so that's very, very important to know the type of capillaries. So these are our platelets. We'll talk about them. All right, so again, what were these cells also that we have to talk about? The B lymphocyte. This is the one that will go straight into the bloodstream, right? So again, what is this one called here? This is called the B lymphocyte. And he will be functional at this point in time. He'll go to mature even a little bit more, though, within the secondary lymphoid organs, like the spleen or the lymph nodes or the tonsils or the galt or the malt, so on and so forth. The T lymphocyte, before it can actually be functional and go to the secondary lymphoid organs, it has to go to a primary lymphoid organ. What's that primary lymphoid organ called? That primary lymphoid organ that it has to go to, first, it overlies the heart. It's in the inferior neck, right? It actually kind of sits within the mediastinum where the heart is. It overlies the heart. This gland right here, this lymphoid organ is called the thymus. And we'll talk about this more in the immune system. But it has to undergo its maturation process. So then when it leaves the thymus and gets put into the bloodstream, now it's mature and now it's going to be called our functional or mature T lymphocyte. But we'll discuss these in more detail. All right, so now we've put all of these guys into the bloodstream. It's beautiful, isn't it? It's not that bad. So now let's talk about the function of each one of these very quickly. So monocytes are super interesting Because when they leave the blood and enter into the tissues, they can form macrophages, which can be fixed, okay, or they can be free. What do I mean by that? So monocytes, whenever they leave the blood, so let's say they leave the blood and let's say they go into the tissues. So say now they're in the tissues. Okay, so over here we're in the tissues. They leave the blood, they go into the tissues, and now they become macrophages. Okay? What does macrophage mean? Macrophage means it's a big eater. It loves to eat all of the certain types of cellular debris and different types of pathogens, right? So this is a macrophage. Macrophages are very, very good at phagocytosis. So what's their good function? Phagocytosis. And they're also great antigen-presenting cells. I'm going to put APCs. It's very good APC. So these are its functions. It's a great phagocyte. It's a great antigen-presenting cell. But what did I want to talk about before was this macrophage can go and get fixed into certain places within the body. What are those places it can go? You know it can go into your central nervous system. And if it goes into your central nervous system, it forms a very permanent resident, which is called microglia. Those are those specific types of glial cells that are present within the central nervous system. Another one is it can get fixed within the liver. So it can get fixed in the liver. And these are called the Kupffer cells. Kupffer cells. Okay? Then it can also go and get lodged within, it can stay within the alveoli. So it can go to the alveoli or the lungs, and it can become alveolar macrophages. And there's more and more that we could do, but we'll finish up here with the bones. And then the bones, a whole bunch of monocytes can actually fuse together. And when they fuse together, they form very, very interesting cells that love to resorb the bone and break the bone down. And that's called osteoclasts. So these can become very, very many types of cells. And we only did a couple. There's even more that we could do. But we're going to just stick to these ones, okay? So again, what do they do? Phagocytosis and antigen presentation, right? And they can be permanent residents or they can be free to roam around within the lymphatic tissues. What is this one called? This is called a basophil. All right, basophils. Basophils, they have these granules, and these granules that they contain have heparin within it. And we already know that from hemostasis, right? So from hemostasis, again, what does it have? These granules can secrete two things. One of these things that it can secrete is called heparin, right? And we already know what heparin does. It's a natural anticoagulant. It enhances antithrombin 3 activity, right? What's the other one? It can release histamines. This is the really important one. And what do histamines do? Histamines they love to regulate inflammation. Inflammation. How do they do that? We'll talk about it in more detail, but for right now, all they do is increase the permeability of the capillaries, and they help for what's called vasodilation to increase the blood flow. But we'll talk about that in more detail. Just know that it's a part of inflammation. All right, what's this next cell here? This next cell here is called eosinophil, right? So again, we already said this was a eosinophil, and we know it's an eosinophil because when you do the right stain, it takes up the red eosin acid. What does this protein love? What does this cell love to do? It loves to secrete proteins. So it has these granules that secrete two major types of very, very toxic proteins. These are very, very toxic proteins. One of them is called the cationic peptide. Cationic peptide or protein. And the other one is called major basic protein. And what are these things designed to do? They love to kill specific types of parasites or worms. So they're very good at killing parasites. So they're very good at killing parasites. Okay, parasites or worms, right? What else can they do? One more thing, we're not going to go into super detail on this, but they do play a role, very complex role in allergies and asthma and stuff like that, which is a type 1 site hypersensitivity. So it does play a role a little bit within type 1 hypersensitivities. But we'll talk about that when we get into the immune system. Just know it plays a complex role in allergy and in asthmas. What's this next one? Neutrophil. Neutrophils are awesome. Okay? What can neutrophils do? They can do so much. Okay? These are the most abundant white blood cells, and we'll talk about a DWC here, the last thing at the end. So neutrophils, they actually can do a couple things. One is they're great phagocytes. So what is one of the big things that these guys can do? They are great phagocytes. You know what they also can call neutrophils? They can call macrophages. So what does that mean? They're little eaters. They're not as good as the macrophages, but they're little eaters. So they love the phagocytose substances. So they're great phagocytes, right? That's one function. Another thing that it can do, neutrophils are willing to give up their life sometimes, right? So one thing that they can actually do is they can do what's called when neutrophils start taking a really, really hardy bacteria or some type of very, very strong pathogen that's hard to break down, they might actually start releasing what's called free radicals. So what do I mean? They can take oxygen and they can convert that oxygen to what's called superoxide. Then they can take that superoxide, maybe even convert it into what's called hydrogen peroxide. And then from here you can get two different things. You can actually go to form a hydroxide radical, or you can actually go to form what's called hypochlorous acid. So now, all of these things here, I'm going to circle them here. Superoxide anion, hydrogen peroxide, the hydroxide radical is the worst one, and hypochlorous acid. This is a really, really bad one too. It's like bleach basically. What can these things do? They can damage DNA, they can damage proteins, they can damage cell membranes, which is bad, which is good for breaking down the bacteria or the pathogen, but it's terrible for the neutrophil because it can actually kill the neutrophil as well by damaging its DNA, its protein, and its membranes. So what is this thing called right here? This can do a process which is called oxidative or respiratory burst. All right, and then there's one more thing that these can also do, and it's called nets. But we're not going to talk too much about that. It's just they can release what's called extracellular traps, where they literally release their own DNA and chromatin material onto pathogens to tag them for certain types of enzymes like cathepsin G. All right? That's that process. Now, let's come to the platelets. The platelets are easy, right? So these are platelets. These are these tiny little cytoplasmic fragments. Platelets. What do? Well, if we watch hemostasis, we know what they do. They play a role in blood clots. So they help to be able to plug blood vessels. Okay, so they help to plug blood vessels to prevent blood loss. Next cell over here. This is called a B lymphocyte. And this one was called a T lymphocyte. What can the B lymphocyte do? B lymphocytes are very, very good at being able to get converted, so they play a role in humoral immunity, and we'll discuss this in more detail in immunity, but what you're going to just need to know for right now is that they can turn into these really, really important cells here, which are called plasma cells. And these plasma cells can secrete antibodies. And these antibodies are important for being, or gamma globulins, to fight off certain types of foreign pathogens. So again, these can help to be able to secrete antibodies. All right, that's the function of the B lymphocytes for right now. There's obviously more that we could do, but for right now, this is the simplest form of it. T lymphocytes can actually divide themselves and go, well, they can form two different lineages, actually three, but we're only going to talk about two here. One is called the T helper cells. So the T helper cells. And what the T helper cells do is they help the B lymphocyte to turn into a plasma cell. That's one thing they do. And they can also react with antigen-presenting cells. They can do tons of things. But for right now, know that they play a role within helping the B lymphocytes to produce antibodies. The other one is called cytotoxic T cells. And these literally induce apoptosis of infected cells. So these induce apoptosis of infected cells like virus-infected cells or cancer cells. Okay? So now, we've gone over all of these cells in pretty great detail, right? Obviously, we'll go into more of them in the immunity. Now what I want to finish up with is, if you take a millimeter cubed of someone's blood, you take a microliter or a millimeter cubed of blood, how much percentage, if you do a DWC, would you get of each one of these white blood cells? All right, so here's a little mnemonic to help you to remember that right here. It goes like this. Never let monkeys eat bananas. All right, banana. All right, so never let monkeys eat bananas. I love Minions, all right? So never let monkeys eat bananas. So neutrophils, how much do they account for? That's what N stands for, neutrophil. They account for about 50 to 70% of the actual white blood cells. Lymphocytes account for about 20 to 30. So again, how much? 20 to 30%. Monocytes account for about 3 to 8%. And eosinophils account for about 2 to 4%. And then basophils account for about 0.5 to 1%. So this gives you the relative abundancy from what's called a DWC. Differential white blood cell count will give you the relative abundancies of the white blood cells, right? And you can just remember, never let monkeys eat bananas to give you the relative abundancy of these. And then in hematocrit, we'll talk more about platelets and their values, okay? All right, guys. So pretty much in this video, we talked everything that we possibly could about leukopoiesis. We discussed in detail the entire leukopoietic process, and we talked about the functions of the white blood cells and their relative abundancies. All right, see you, Ninja Nerds.